All right, so let's take a look at the machine vision. Now, the first one, you just fit a line through some points, which is just kind of a conceptual idea to see how it works. Now we're going to solve a more realistic problem, recognizing clothing items. Here's one of the famous AI training models, a bunch of little photographs of clothing, and they fit in 10 categories: trouser, pullover, sandal, sneaker, bag, and so on. And we're going to train the AI to analyze those images. Now, the way it works, it's going to take each pixel as an input and then pass it through a couple of hidden layers of neurons to do the job. And here's a summary of it. The input comes in 28 by 28 pixels in grayscale. So you have 784 pixel values, each of which goes from 0 to 255 in just a brightness measure. Then it's going to take those 784 inputs and just treat them as independent pixels and pass them through one hidden layer of neurons, and then sort them into 10 output neurons, which will be the probability that it's in those 10 categories. Now, by the way, I used to do brain models, and I want to point out this is really, really stupid. You have taken every pixel and treated it as an independent measure, and that is crazy. That is not what your eye does. What you ought to do is find edges and shapes and then pass those up to a higher level. The fact is, it doesn't remember in any way that this pixel is next to that pixel, and having those two pixels both be dark means there's a line here. Instead of two randomly placed pixels, it just treats every pixel as an independent, uncorrelated event, and which is kind of stupid. And expecting the neural net to figure that out with only one layer is also kind of stupid. But we're going to see how it works. And this is where I want to point out something else really important. Neural nets do not work the way your brain does. The human brain works this way. It finds the edges, it finds the shapes, it says, this is the background, I can ignore all of those hundreds of pixels. This is the image, there's a black stripe here. You know, you work by finding features, but the neural net does not do that, and that's going to be important later when we fool neural nets. Errors that would not fool a human will fool the machine learning because it has learned a strange way to do this task, very different than the way a human would. Anyway, the coding is very simple. Just like the coding we did before, we use this Keras model again. So we have an input layer that's 28 by 28 pixels. Then we have one hidden layer with 128 hidden neurons, and then 10 output neurons, which are going to be the probability that it's in each of those 10 categories. So not much at all here. I'm going to make a new notebook and close these old tabs. All right. So there's all the code it takes to do it. It downloads these images. They're in some database it can get at easily, included in Keras. And so it's going to fit and evaluate the model here. It's just allocating some RAM and disk to me still. You can tell what it's doing. And then it shows a little green arrow where it is. Now it's importing the library. And you can see how long it's been, 10 seconds, 11 seconds. It's really pretty nice. You can see that, and here it is going. It's preparing the training images by normalizing them. Now it's fitting the model. So it's going to be going through epochs of training. It's going to do 5 epochs, and each epoch takes some time now. Last time we did 500 epochs. Now we're only going to do 5, and they're taking a lot more calculation for each one because it's a more complicated model. But you can see that it measures the loss here, which is how many it got wrong, and it's going down. It was 0.6, then 0.3, then 0.33. So you see, it is converging. And we're going to do 5 epochs of training. And see the loss is still falling. After 5 epochs of training, it's going to evaluate the model. So it gets accuracy goes up to 89% on the training image and 88% on the test image. What you do is you break things into training and test images. So I take typically something like 80% of them you use to train, and you hold back 20% and feed those to the model so it sees images it has never seen before, and you test to see how accurate it is. That is the way you make sure it's learning the underlying trend of the population. If you have overfitting, you'll get the training data will be very accurate, but the test data will not be accurate. So it looks like this is pretty good. We have 89% on the training data and 87% on the test data. So we might have a little overtraining, but not too much. Now, let's look at how well it did. We're going to look at the results for the first 20 images. Since the accuracy was only about 90%, we should be able to find a few there that it got wrong. So this is going to just show the results. And what this is, the first number is the correct answer, which category, and the chart is the probability. So this first one was really a number 9, and it had a 97% chance of being a number 9, so it got that one right. If we look at this 51, it might have got that wrong. No, it got it right. This is number 6, 0, 1, 2, 3, 4, 5, 6. It had a 51% chance of being 6 and a 41% chance of being 0, so it almost got it wrong. This one here, it might have got, yeah, this one here it got wrong. It's really a 7, 0, 1, 2, 3, 4, 5, 6, 7, but it categorized it as a 5. So that was a mistake. Now let me figure out which one that is. I didn't put numbers here. That would have helped. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I think it was number 12. Either 11 or 12, it got wrong. So I'm going to print out those images so we can see them. I'm going to print out both 11 and 12 because I'm not sure I counted that right. Either 11 or 12, it got wrong. So I'm going to print out number 12 here. 12 and 11. All right. Okay. And the categories was between 5 and 7, and I think that's the difference between sandal and sneaker. Yep, sandal and sneaker. I don't know if I could tell a sandal from a sneaker either, and clearly, I think it's this one. It can't tell a sandal if that's a sandal or a sneaker, which I can understand. Well, this one looks like a sandal. That might be. Anyway, one of these shoes, it couldn't tell if it was a sandal or a sneaker, so it's kind of understandable why it couldn't tell based on the training. Those two shapes are quite similar. All right. And so now we can train it for more. So let me go back here where we trained it. And instead of training it for 10 epochs, we're going to do the model fit and train it for 25 epochs. Let's try that again. Each epoch is taking about 7 seconds, so about a minute to do 10. So maybe 2 or 3 minutes it'll take to do 25. And I'll just go ahead and look at the answer here. The answer is, of course, it ends up being more accurate on the training set, but less accurate on the test set. That's overtraining. It's now fitting the noise, the specific details of those training images, and it's not getting any better at fitting the test images. So that's overtraining. All right. And now, let me get this thing back. There we are. All right. So we can summarize it, and that's just a way to find the flags. So that's all there is for that one. And I want to mention the other computer vision ones you can do here. That one is interesting to get you started. The next one, you break a CAPTCHA. So here, they have a very simple CAPTCHA, which just consists of letters that are in different fonts and tilted over sideways. And you can train it to recognize those letters the same way. You have 26 letters and digits or something, so there's a total number of images, and you can train the AI to do this. This is why all these CAPTCHAs are pretty much broken now. AI is good enough to do them all. The whole point of them is that a human can solve these puzzles and computers cannot, and that is emphatically not true anymore. Every known CAPTCHA, there are ways to do it. This is why you don't see these things as much as you used to, because they're not as effective as they used to be. So you can train this CAPTCHA and see how accurate it gets. And the next one amazed me for machine learning, where you de-blur images. This one here, I never would have believed this would work. This is, by the way, how Stable Diffusion and other image generators on the web work. What you do, remember I said in the early presentation, you can take unlabeled data and make labeled data by manipulating it. So if I want to train something like Midjourney to make a Picasso, I take a real Picasso, and then in 1,000 stages, I add more noise to it. So it gets blurrier until it's all noise. And then I train a machine learning model to remove the noise. And then to generate a new Picasso, I start with random noise and de-blur it until it turns into a Picasso. If you'd told me about that, I would have said that's impossible. That would never work. And even if it did work, it would take so much processing time, you could never afford it. And it does work. You can do it. And it's so cheap, you can do it with a free Google Colab machine. So that's what this does. We import images. These are images taken with real cameras. Somebody took a few dozen images with a camera and then deliberately put it out of focus so you could practice taking the blur out of it. So you load a bunch of these images and you train it to de-blur the image, starting with images where you know what the de-blurred image is. And this has a 17 million parameters in this model because it's taking full color real photographs and de-blurring them. So you train the model. Now, if you train it for 5 epochs, the result is it takes 5 minutes to go through 5 epochs of training, and the results are unspeakably terrible. Here's what you get. Here's the blurry image, the sharp image, and here's the supposedly de-blurred image. So 5 epochs of training is not enough to do any good at all. It's a terrible approximation. So the next step is to improve it. And I was actually, the original version of this project I wrote, you would give it more training and you'd have to wait 74 minutes for it to train. And then it would work. But what one of my students pointed out, which I didn't know, is not only does Google Colab give you free processing, it even gives you access to a GPU or a TPU, a graphics processing unit or a tensor processing unit. Although they'll only let you do it a certain number of times before they start blocking you if you don't pay. But if you do that, use a GPU, now it moves really fast. And now you can do 100 epochs of training and it only takes like 5 minutes. And after 100 epochs of training, it actually does this job pretty well. Here's the blurry image, here's the sharp image, and here's the de-blurred image. It really does a pretty good job of removing the blur. And this is something I see on all the TV shows where they have a surveillance camera with a picture of a car and it's blurry or a face, and they say, de-blur that. And they can de-blur it. You can do that. But remember, the warning, it's not really able to de-blur accurately. It's guessing what features are hidden behind that blur from other images. So if you have a blurry picture of a face and you de-blur it, it will see a sharp face, but it might not be the right face. And there are all these scandals where facial recognition has led them to arrest the wrong person. So again, it's kind of a swindle. It looks better, but it's not necessarily really getting closer to the actual image. It's just guessing what it thinks should be there based on what images it was trained on. But anyway, I was amazed by that. And there's various versions of this where you can see how it works. So you might want to try some of those image processing ones. That's, like say, probably the most mature form of machine learning right now, according to Gartner, is this image processing. That stuff is really working. We're done with all the nonsense of expecting too much from it and being too angry at it and getting down to like practical tools that do some good. So check that stuff out. I'm going to stop this video.